Thank you, Yasmin. Thank you for the introduction, and hello, everyone. Welcome to this, the second installment of my HBase talks. Today we talk about HBase Coprocessors, a fairly recent addition to HBase, and I think a very exciting technology that you could use in the future to implement things that weren't possible before or quite cumbersome to implement. So that's our today's topic. So let's get started. A quick one about me. We should see the slides. My screen is a bit slow. I hope you're seeing the slides. Mine is still loading. I'm a solutions architect at Cloudera. So my daily job is to work with customers and work on problems in all the Hadoop ecosystem. This includes HBase and everything around Hadoop, like Pig and Hive and all these other things that are quite exciting at the moment. I'm also the author of HBase, the Definitive Guide. So if you're interested, there's a book out on HBase. A lot of what I'm talking about today is in there as well, with more text to it. So feel free to have a look into that and read up on it. I'm also quite happy if you have feedback for me. If you find something in the book that doesn't make sense, or you would like to see expanded, please let me know, because I'm hoping I have a chance to work on a second edition, and then I'm very happy to bring in your ideas. I'm working with HBase since 2007, so end of 2007. So that's basically a few years back now. The HBase has since matured tremendously, and I'm happy for everyone to start with HBase today, because back in the days there were lots of things that you had to go through and just sit out or fix yourself, because there were issues depending on your use case. And nowadays HBase is much more mature, and you can start using it out of the box. I'm also organizing the Munich OpenHUG User Group meetings, and I'm a speaker at conferences like FOSDEM or Hadoop World next week. So that will be soon. So if you at Hadoop World, please do come by and say hello. We even have book signings there, so if you're interested, you could even get your book signed. Quick overview. So Coprocessors is something that has been added to Bigtable, which is the foundation for HBase. Fairly recently, in terms of history, when you look at Google and Bigtable, Bigtable is around for at least since 2004 or 5 at Google, and 2006 the paper came out, 2007 HBase was implemented. But in a talk in 2009, Jeff Dean mentioned Coprocessors as an addition to Bigtable, because if you use Hadoop or Bigtable, you find that over time you're in the need of locating not just the data basically, and having the region server serving the data directly to the client, therefore just nicely distributing your data and your access over many servers. You also find that it would be nice to move some type of code towards the data. That's very similar to what you see in MapReduce. MapReduce also has this idea of where you take the code and execute it where the data lives. So this is basically the same sort of concept. You need something that can run on the servers to avoid the network traffic round trips and things like this, and extend the functionality. It runs user code within each region of a table. So the code that is deployed splits and moves with every region. So it basically is attached to a region, so it can move around. That's not terribly interesting or so. It's just interesting that every code basically sees its own region and can work with that. The calls to coprocessors is usually addressed for a particular row or ranges of rows. So you do not have to deal directly with regions. You can just basically still talk to row keys, ranges of rows, and the client library takes care of resolving where to go, where the region is, and executing the right coprocessors with the region that you're addressing. It automatically scales, has this implicit automatic scaling feature, but also has load balancing with it, because as regions split and divide to handle growth, and load if you want to. If we proactively split a region, then the code also moves with it. Means that now you can talk to smaller ranges of keys and therefore have the code do less work. So that's quite interesting. Also, it has this built-in request routing that I mentioned, that you do not have to deal with where the code is. You just basically execute the function, and the client library takes care of the rest. An example use case, or example use cases that I mentioned in that talk by Jeff Dean, were that if a big table, they use coprocessors to implement scalable metadata management. That's for Colossus, for one of their products there. So they're using it as a backend to store metadata, but in a way that automatically scales with the system. So that's one of those use cases. Also, Google Translate uses it to build the language models for the machine translation. So they support these projects within Google by implementing code directly on Bigtable that then can be executed close to where the data lives. Another one is the support for distributed querying and query processing for full-text indexing. So another quite interesting topic. Indexes, in general, is an interesting topic with Bigtable and HBase. So that's another probably probable use case. And regular expression search in code repositories. So Google Code probably is using it so that you can actually type something in and distribute the search across all of the regions, or tablets in their case, and search for the regular expression term and return the results very fast. That again makes use of the scalability and the ability to send these queries to all of the regions in parallel. So it's a quite powerful feature. You could think of it as something like MapReduce jobs over HBase, which where you often only have map-only jobs. The reason for that is that if you have HBase as a data source for MapReduce, it's typical that the row key for a table is already sorted and is distinct, because that's your primary key in a table in HBase. So your primary index or your primary key in the table already has these qualities. So it's not that typical that you have to go into a reduce phase, because the reduce phase is usually where you get the sorted results. So you make use of the map and reduce functionality and the sort and shuffle in between to do the sorting for you. But in this case, is often not typical for MapReduce that you run over HBase, because you can just read the entire table, distribute it in many mappers, a mapper usually per region. So you're distributing the load over the cluster, making use of the MapReduce cluster more or less as a multi-threaded distributed machine as its inherent features of sorting data and then going into reduce phase to output an end result. So you can sometimes, in some of these cases, coprocessors can completely replace these jobs. You don't have to go out and run MapReduce, but you can actually do this with coprocessors, especially in smaller clusters where you have co-located MapReduce and HBase and HDFS on the same cluster. You have a lot of moving parts and you struggle for resources. That's a good option to get rid of the MapReduce part, MapReduce framework. Don't start even those daemons, and use the coprocessors to do the work distributed on the regions. So that's a very powerful replacement. So what I'm going to do is as I go through the coprocessors, I circle around once or twice or even 3 times, repeating the sort of layout of coprocessors. But every time I do so, I go a bit deeper into the topic. So I'm first give you an overview of coprocessors and the pieces that are important for it. But then I will basically go back and say, okay, now we know all these pieces. Let's go and have a look at how they work. And then as we go along, I actually show you how you can implement one of those and deploy them on your server. So that's the goal for today, is that you can see how to write your own coprocessors. HBase coprocessors, in comparison to Bigtable's coprocessors, obviously they're inspired by the same. We do not have too much information on the Google coprocessors. So we know the general idea from the talks. We know what they are used for, but we do not have the full understanding of how they are used and how they are implemented for a big table, because there's no paper on it, as the big table paper fairly detailed describes how big table works. There isn't anything on coprocessors, but the general idea is understood, and this general idea is implemented or will be implemented in HBase to a degree. Whatever is needed, we will implement. You will also see that there's a lot of things still missing, so it's a very young addition to HBase. It has been implemented to a degree that's handled what was needed, but I'm sure there can be, there's more to be done, and there's more ideas could be brought in. So please do so if you use coprocessors down the road and you feel like something is missing. Please do report back, because as I said, I'm sure there can be a lot of things can be just added or easily added or should be added. So the coprocessors define various types of server-side code extensions. So we have different types, different things that you can extend on the server side. And they are associated with a table. They run with a region, but they are declared either on the table as a table property, or if you want to, as a global one for all tables. So there's two ways to do that. We will see this as well later on. They are implemented as Java code, so currently the only way to implement coprocessors is using Java and compiling them into a jar file and then deploying them on the servers. So one of the attributes that you have to put into the table is the path to the jar file. So you have to deploy that really on the server. Again, we will look into this in a minute. The jar is then loaded as the region server, as a region is opened by the region server, and it blends the new functionality with the existing one. So it makes this new functionality available without changing the old one. So it keeps the same API but extends only, so it just blends in quite nicely. And it's quite interesting that with coprocessors, they can usually be chained, so you have priorities and a load order. So within a priority, you can have different coprocessors that get executed first by priority, and within each priority they're then executed by the load order. So if you have the same priority and you load them first coprocessor A, then coprocessor B, they're declared in that order, then they are loaded that order and executed that order. So you can chain them and do some interesting things with them. We'll look into this as well. So they allow altogether, they allow for dynamic RPC extensions. And again, we will see how to do that. The next slide, I have to wait, here comes, the coprocessor classes and interfaces. So that's sort of the high-level view on the actual classes, or the hierarchy of classes that you have available in HBase. So the coprocessor interface is the one that you have to inherit from. The coprocessor interface is the one that you deal with, that you have to use to implement your own extensions to HBase. The other two that as you see there as well, those you usually don't have to deal with, and you can't really deploy them without changing. There's no way to declare them as being custom and load them, but they are there for you, and they are ready implementations for you. So there's, for example, for the coprocessor, there is a coprocessor environment. The coprocessor environment is the one that retains the state across invocations of coprocessors. So it's like where it's embedded in, it gives it the memory. It's a predefined class, as I mentioned. I have a list as well, and there's also to support this or to run everything together is the coprocessor host. So the coprocessor host is what ties the state or the environment and the user code, your coprocessor, together. So that's, again, a predefined class, so you don't have to deal with the last two. They are there, and they automatically happen for you, and we will look at what they provide to you. But the only thing that you really have to deal with is the first one, the coprocessor interface. So it's altogether a quite simple class layout. So it's not a lot of things, a lot of moving parts, and it's fairly straightforward to implement. It's quite an interesting observation, because it doesn't add a lot of complexity on the class level itself. I mean, there's more to it, but there you are. The coprocessor itself, the interface, also defines what I mentioned earlier, the priority. I printed out the code here. As you can see, there's a numeric priority. So there's a system and user priority. You can see that the highest priority is 0, and the lowest priority is integer max value. So it's like a very large number. The numbers itself are ranges, and you can see that the user priority is everything between that highest number and the half of that highest number, the half of it. So any number in between that you choose when you deploy, as I mentioned, we have this in a moment. If you deploy a coprocessor, you can use these priorities to build groups and say, okay, I have a priority that is executed first, therefore you have to fit them into that number range. The system priority is something that you can, to a degree, influence. You can have your own system coprocessors, but there are also some that automatically loaded, and you will see how this works. But for now, the priority is the one that you use to, you just have to define a number and assign that to your coprocessors. And the coprocessor environment is the next. My load is a bit slow here, hang on. Don't see the slide yet. Come on. So the coprocessor environment is the one that I mentioned earlier, which it gives you the state of, or the memory of the coprocessor. So every coprocessor that you create, every coprocessor you write, has its own environment with it. So the coprocessor environment is instantiated per coprocessor. So this is why when you look at this, you have coprocessor get instance to get the coprocessor instance if you have the environment. You can talk about the priority. Here this is slightly outdated. This is from the book, just letting you know. I put this into the errata there. This has been changed after the book has been printed. The interface has changed, and the priority, which was previously in enumeration, coprocessor.priority, has been changed into an int. So now these are just numbers. Here you see it's just it was still the coprocessor.priority. Now it's a constant, or it's a constant or like a number int. And as I said, I put this into the errata, so just so you know that in the book there's already something outdated because that's still in flux and heavily being developed. So this is one of the few things that isn't current. But I think that is pretty much the only one that we will encounter today. This has an impact on a few things later down the track, but I will mention this as we go along. You can also get, what is interesting here, the get table. You have a way to query from the coprocessor environment and a table instance of any table you want to. So within your coprocessors, the coprocessor environment is the one that gives you access to the tables that you want to talk to. So if you have to do some loading, some updating, whatever you need to do, this is basically a way to do this. The reason here is that you do not want to create your own tables, because this table here that is returned by the coprocessor environment is a special one. It has a few features removed, certain things that do not make sense as a coprocessor to execute, they are disabled. So this is the only way to do this. Currently, again, you could go ahead and create your own tables, but in the future this will be denied or will be forbidden, and therefore if you want to implement a coprocessor today that has or is maintainable for quite some time, then you're highly advised to use this interface to get the table. Now we have the coprocessor host. The coprocessor host is, as I mentioned, the one that ties the state and the coprocessor together. So this is the one that keeps all of the coprocessor instances and the environment together. So every region server has or every region has a coprocessor host, or indeed multiple coprocessor hosts, that keeps these things together, so that when something executes in different ways, they are always live together in the host. So the host is the central one that it maintains those classes and their state. The concrete implementation that I mentioned earlier, that you don't have to really implement your own, is because there are already three of them. One is called the master coprocessor host, the region coprocessor host, and the well coprocessor host. So the well, that's for write-ahead log. The write-ahead log is the one that writes like a binary log within each region, every modification first into this binary log before it's actually then kept in memory and flushed to disk later. So you have a way to interact with the write-ahead log. So that's quite deep down in the guts of HBase. The master one is the one that lives on the master side and it's only instantiated within the master, and the region coprocessor host, this is the one that is instantiated for every region on the region server. So you will find there's one master coprocessor host in reality and many region coprocessor hosts because there's one for every region. So that's sort of the trinity there of classes. So you don't have to do anything there. They are there for your usage. They do have specialized environments. We saw the environment earlier where you can get the table, but you will see that there's also specialized ones that you can use to get more information depending on where you're running. We will look into those as well. Next thing is the control flow. It's a bit small, unfortunately, but I hope on your screen it's larger. Mine is a bit small. You can see here how the client interacts doing normal calls to the server. In this case, for example, these CRUD for create, read, update, or delete, where you have these typical operations in HBase with the client API, and you can see the call goes into the environment there, or into the region. It goes into the host. The host then goes through the region into your coprocessor code and then goes out. And you can also see in this picture how this is already done for every region separately. You can see there's an instance of the coprocessor host per region in the region server. And what you can also see is that these are actually chained. So based on this loading priority, or the priority in the loading order that I mentioned earlier, you can see how the first one is called, and the result of the first one is actually passed on to the next one. And the first ones being called are, and that's basically quite obvious, the system ones. So before the user coprocessor ones are called, the ones with the priority user coprocessor, all of the system coprocessors are called first. So these are the ones that have the highest priority, and then they have all of these being called as they are loaded, or if they have in the order they have been declared. And then once they are done, they pass on their calls to the user ones, and the first user coprocessor is called, the second one is called, and now the last one, as you can see, does the actual interaction with the region. The last one, in this case here in this picture, is user coprocessor 2, is the one who does actually the call to the region itself in this case. For instance, if it's a coprocessor that does a certain operation before, for example, a get operation, you have a way to sort of interact with that beforehand. Then you can, the last one is calling the operation on the region, and then chaining it back to the client. So that just gives you an overview of how the coprocessor control flow works. So it's involved. You would still probably start only with a single coprocessor first, and then you don't have to worry about this because you only have one. There aren't any system ones by default. You have to keep this in mind. There isn't any one that are supplied with HBase. There will be a few in the future, but currently there aren't any available. So you just start with one, and you add a few more and get used to the actual chaining. And I will show you as well later down the slides here how you can make use of that one in a chain and how to interact with the chain. That's quite powerful. Now we circle back. So you have seen sort of the flow and how they are structured, like how the the coprocessor, its environment, is tied together by the host within each region. So I'm focusing a lot on the region one because they're quite common, but I also talk about the master one. The well one I leave out a little bit because that's just another one. You just have to look into what it provides, and it works exactly the same way, but due to time constraints, I'm looking mostly at the region one and a bit at the master one. The coprocessor, so circling back, the coprocessor interface is the one that you have to deal with. That's the one you have to implement for your own code. The base, it is the base for all of the types of coprocessors. So I'm currently always talking about coprocessors as one thing, but there are actually a couple of variations of coprocessors. And the basic one, or the base one, is always this interface. So that's the one you start off with. And it provides not just the priority, as we saw earlier, it also has a start and stop method that you can override in your own code to use it to do lifecycle management. So you can, in start, you can ramp something up, and in stop, you can ramp something down. So if you have resources that you have to talk to, you can use these methods to interact with the lifecycle. And the lifecycle is also defined in this interface. It's listed below there. So you can see there's a couple of stages a coprocessor goes through, from uninstalled to installed, then starting up, then it's active, it's stopping and stopped at the end. So that's sort of the lifecycle of a coprocessor. And you have these start and stop being called as you see it in the table below. During the starting, the start method is called, and during the stopping, the stop method is called. And once the stop method exits, it goes into stopped. So you have ways to interact with when classes are loaded, and you can construct something and ramp something down in the end. The observer class. So now I said there are multiple different coprocessors. Coprocessors fall into two different types, mostly for HBase. The first type that we look into is the observer class. So the observer class or classes are the ones that are comparably to something you could call a trigger in a typical or in a, let's say, traditional RDBMS in a database, where you have callback functions or hooks for every operation that happens, that when you execute something, when you do a get or whatever it is, you have a way to hook into the call, and you can decide what's going on during that call. So that's how you can look at that. It's not just the explicit API calls, not just when the client says, oh, get me this row, or put this row, or delete this, do that. Also for important internal calls, things that happen asynchronously, there are triggers as well. So you can use this for your own implementation, and I have an example of that later on. The concrete implementations of the observer here, they are, as you see, that we have the same sort of trinity here as we saw before. We have a master observer matching the master coprocessor host. So the master observer is one that you implement to provide hooks into the HMaster API. So these are sort of the DDL statements. You have the region server, region observer. That's the one you use to implement code that handles region-related events. And you have a while, like the write-ahead log observer, which is the one that you implement for anything that is related to the write-ahead log. Okay. Sorry if I make pauses here. It's just I'll wait for the slides to show up. I'm hoping you're already seeing them. You can already read. Okay, here we go. The region observer. So it's just, as I said, I'm concentrating a bit on the region and then a little bit on the master. So the region observer is quite a common thing that you want to look at, because that's sort of the one that make a lot of sense to implement as a start. So this is one that we should start as well looking into first. The region observer is quite powerful. It can mediate or veto actions. So what you can do is you can implement this, or you can implement in this case, security policies. You can check certain things and deny actions, for example. You can also use the priority to have mediators run first. So you can implement something where you have a global or a low-level check that runs before all the other checks run. And then you can decide in the mediators if you want to do something that avoids any further execution down the chain. So that's a very powerful way to interact with the coprocessor chains. It hooks into all of these CRUD plus S, for the lack of a term for it, because in HBase we have the typical get, put, delete, but we also have a scan API, we have an increment, so it should be a CRUD plus SI, and there's a couple of other ones like the atomic operations, the check and put, and check and delete. So there's a couple of ones that you can hook into that aren't part of the normal CRUD APIs, but all of the ones that you find in the HTable API, the one that the client uses to interact with data on the server side, for all of these functions, you have a hook on provided by the region observer for you that you can use to interact with these calls. You can also see here listed, for example, flush, compact, and split. So these also are functions that you can issue from the client side. These are more advanced. They're more like admin API, but all of the client API functions, and not only the table-related one, but also the admin-related one, the administrative functions, have a hook on the server side. So using coprocessors, you can interact with those. Now, for every call that you find in an API, for every HTable call, for every get, put, and whatever it is, then for every flush, compact, and split, you have a pre and a post hook. So you can have a hook that is called before the action, and it's called after the action. So you have a way to say, I'm checking something, the pre first, to do a mediator, for example, to deny access or to check what is being done. And you can then say, yes, this is okay or not. Or you can have a post hook where you say, oh, the client just tried to load a certain row. Let me just modify this row by modifying a column on the fly or decode on the fly. So this could be used, for example, to do a on-the-fly compression, decompression, or encoding, decoding, serialization, deserialization. There's a couple of ideas that you can implement there that are then transparently called because these triggers are called on the server side. You don't have to invoke them. They're automatically happening. They can be used to build secondary indexes where you can, when something is added to a table, you can update a secondary index. Or in the future, there's an open Jira for filters. The idea is that in the future, filters are also implemented as coprocessors because they have state, while the old filters didn't. And so it's much more powerful that way. The next type of coprocessor. So coprocessor is a low interface that you need to implement, but on top of that we had the observer classes. Now we also have the endpoint classes or the endpoint class. So anything implementing an endpoint is something that is different from a trigger. An endpoint is something that extends the RPC protocol with a dynamic function so that you can use it between the client and the server to execute any arbitrary code that is loaded in the region server. So you can just deploy the code, you have a proper function to execute this, and then you can execute that code. What I mentioned there is that when I said any sort of arbitrary code, there are plans in the future to do any sort of safekeeping, sandboxing that is possible with Java to a degree. We have to think about what is practical, what isn't. But the point is in the future that the idea is to use something like ASM or so to do code inspections, code weaving, to introspect or to identify malicious code and being able to deny execution or guard against CPU usage, kill runaway codes. You could have an endless loop in your code. We need to find out there's an endless loop and abort the function to protect the server. Currently, whatever you write, you're on your own, which means you could do anything you like. because you have the control over your code. This is not for someone to give it to end users currently. This is something that you would create to use it in your own environment or in your own project to extend HBase. But currently you cannot really give this to anyone to build arbitrary code and load this into the server because there is no real checking going on. But as I said, plans are there, but no one has implemented this yet. Steps to add your own is also what you have to do. You have to define and implement your own protocol to implement an endpoint. So you create a protocol, and then when you have the protocol, you implement an endpoint coprocessor. So you just implement this class, and then you can execute it with two different calls. HTable has a coprocessor exec and a coprocessor proxy, and I have more on that one later. So it's fairly straightforward, protocol definition, implementation of the code, and then execution from the client side. So it's very straightforward. Coprocessor loading. So how do they get loaded? There are two ways to load them, dynamic or static. Static means they are added to the configuration files or the table schema, which means they are loaded when the table is opened or when the regions are opened. In the future, there's plans to do this dynamically, where we load them as dynamically, saying, okay, just open we just say deploy this coprocessor, and it's pushed out to the servers or opened up in the servers. All of this is quite difficult because you have to make sure that all of the regions out there that are currently live load that class, make this available, and since that isn't really too easy doable, there is no current way of dynamically deploy coprocessors. So at the moment, you have to pre-plan and you have to modify a table, which means you have to take it, you have to disable it to modify it. Static loading is the way that it's being done. Is you load this basically from in the order they are declared in the config file. There's a special property for each type that we saw before. The regions related one gets loaded into for all of the regions, and the priority is always system. So whatever you have in your config file is automatically system priority, and the jar must be available to the code. And I have an example here, a quick one. There's an example code. You can see this is from the HBase site file. The HBase site file has these three types of property keys, and I declared a couple of coprocessors here. You can see that there's a region one, a master one, and a val one for every type, and they're only loaded where they are needed. So the master only loads the master classes, the region server only loads the region classes, and the val class loads the val classes. So you can declare them all in one config file, but they're only loaded where they are needed. So the coprocessor loading continued here on how this works. We looked at the static loading from configuration. The other way to load them is using a table schema. So you have a definition here per table. So you have a way to declare coprocessors within a table definition. When you declare them per table, they're automatically assigned to all of the regions for this table. So the ones from the config I mentioned are for all of the tables, for all of the user tables, while the ones per table schema are only for a specific table. So they're more targeted, and therefore probably the one that you want. Otherwise, you execute these coprocessors on all of the tables, which might not be what you're planning. They're only region related, so there's no val or master, obviously. I mean, because they are per table, so these are only the region coprocessors, or region observers in this case. And you have to alter the HTable descriptor and add those. So you have to disable the table and then alter the table descriptor by adding this. And there's an example. So you're adding a key, which is has a prefix of coprocessor, a $sign, and then a number, and then you specify as the value the path to the jar, the class name, and the priority. And this is a bit abstract. I have an example for that here on the next slide. Here, for example, you can see I declare a coprocessor 1, coprocessor 2. One is a coprocessor that actually resides in HDFS, and one that is on my local file system. Might make sense, might not make sense. It's something, obviously, typically you have your coprocessor code in HDFS, and then all of the region servers have access to it. Otherwise, you have to make sure that they're all deployed locally to each machine. You declare the class, the coprocessor.test, coprocessor.another test, and the priority. So I have 10 and 1000 here. So these are all very low, so they're slightly over 0. 0 is the highest priority, so these both, because they are less than a quarter of integer max value, these are all considered system priority. In this case, because I only declaring my own coprocessors, and I do not share with anyone else, and there aren't any system coprocessors that are coming with HBase, I'm fairly free to use any sort of range I like. That's something you can work with, and you can change it later on if you need to. Sure, you have to disable the schema, so that's something that you have to keep aware or keep an eye on. But you can do whatever you like on this end. If you want to have anything that is considered user coprocessor priority, then you would have to add that very high number of at least half of integer.max value and put these numbers in there. So that's how you declare them. Here's an example now, adding a coprocessor on the fly. Again, this is taken from the book. I won't spend too much time on the examples given the time that we have, but this shows you basically how the path is basically taken from HDFS, constructing the location of the jar file, getting the descriptor, putting in the coprocessor key with the value that we discussed earlier, and here I'm actually putting in not a number, I'm putting in coprocessor.priority_user. That's the new style, so that's already showing you new style declaration here, and declaring the table, creating the table, and last line in that example, I'm getting the table descriptor back from the table just to confirm that it has worked. So on the next page, you can see the results. So that's the printout of the example. Again, that's in the book repository. You can run this as is. Just download the GitHub repository and run this, and it will work for you on HBase. You can see it prints out coprocessor has been declared. There's the file test. It's a coprocessor, and you can see the half the integer.max value. So it's a bit of a large number, but there you go. Next one, region observer. Going back to where we were, so we said we looked at the region observers, we looked at the endpoints, we looked at how to deploy them just by declaring them per table or in the config. Now we're looking a little bit deeper into what you can do per type. So here's the region observer again, so we're circling back, and I mentioned it handles all the region-related events, and it has these sort of two types of operations. One is lifecycle changes, one is client API calls. So there are pre- and post hooks, as I mentioned as well, which you can use for secondary indexes. So that's quite it covers the entire API that you find from the client side. As I said, the table API and the admin API. It also handles these lifecycle events. So the coprocessor hooks into the open, pre-open, open, and post pre-close events. So you have the pre-open, post-open calls that you could hook into. So before a region gets opened, you get a call if you want to, and before it gets closed. So again, you can use it to ramp things up. I have an example here. You can piggyback or fail the process. For example, you can do a cache warm-up after region has opened, or you can suppress splitting and a few other things in other events. So just saying that you have not only the start and stop of the entire coprocessor lifecycle, you have also a per region lifecycle you can hook into and trigger certain events. For example, warming up a cache. Here, a quick overview of, again, it's in the book and in a Java doc or so, and in the code, so I won't go into all of these details. There's a lot. Just saying there, the region environment is a specialized environment. I mentioned earlier you have this coprocessor environment, which has the get table, which is the one that you want to use to retrieve a table reference. You also have this region environment, which is a specialized one, which gives you access to, for example, the region you're currently in, region services. And the region services is listed underneath. So the first table is for the region environment. The second table is for the region services. So this is the one that gives you access to a couple of low-level classes like the flush requester, a couple of other ones that you could use to handle specific things, and that's way beyond this talk, but you have access to pretty much everything on the server side that you need to interact with the server. Looking at the actual pre-open, post-open, like the ones that I mentioned that you can override in your region observer, you see there they always get a that region coprocessor environment variable. So they always get this as the first parameter in your call. So your call, the pre-open and post-open that you implement, the first parameter, or the only parameter in this case, these calls don't have any extra parameters, always get something that's called an observer context. So the observer context is the one that is, as you can see, is related to the coprocessor environment. That's the one that you use to retrieve all of the details. So when you are called, you get always the context, and you're dealing with the context. That's similar to the MapReduce API, the new one, where you get a context and you can take it. It can take the counters from it and increase counters or do all sorts of things. So every time a method is called, you can actually react to it. And here you can see the observer context. That's the default one. So you can get the environment. That's the one that you need to then talk to, for example, the region observer environment. You can have these specialized calls there that you need to interact with the chain. So there's the ones that we want to look at is bypass and complete. So there's a bypass and complete, and I have an example for that. So the bypass and complete calls of the observer in your that you get into your call, you can use those to actually end the chain of the current processor. For example, you can call complete, which completely stops the chain. So if you're a mediator and call complete, then nothing happens afterwards. No other observer in the chain that has the same priority and is basically a low priority that should be called on the same event. None of them is executed. The complete just stops the entire processing and returns to the client, or moves on, basically, whatever the stage is. The bypass is slightly different. The bypass calls all of the coprocessors, but it does not invoke anything afterwards. So you can sort of tell the chain, okay, go ahead and do whatever you have to, like execute all of the other ones, but it will never go to the region and execute, for example, in a pre-get. It will never execute the actual get operation on the region. It will only execute all of the coprocessors in the that have implemented the pre-get. So they all have a chance to add or contribute to the result, and then it returns straight back to the client because you say bypass the original functionality. So we have two ways of interacting with the chain of command. Here's an example. So in the pre-split, for example, I have this observer context, and I just call e.complete, which means I'm deactivating all of the split functionality. So that would be completely disable the splitting on the server side, because every split that would asynchronously be started would run into this coprocessor on that table where you declare this, or on all tables when this is a system-wide or a coprocessor that has been declared in the config, and you would basically disable all of that functionality. You would have to deal with it differently. So that is dangerous. Don't do this. Just an example of what you could do. And because even your manual splits that you invoke from the shell won't go any further, because they also invoke the split functionality on the server side, and therefore would not go through. So this would mean your tables will never split, even if you invoke this manually on the shell. So that's quite dangerous. Next thing. Waiting again for the slide. Come on.
Hey, Hey, Lars, this is Yaz, your host. While we're waiting for your slides to refresh there, I just want to let the folks know, time is starting to tick down. So if you do have questions for Lars and all the fantastic things and knowledge and information he is showing you today, please type those into that group chat widget. It's that red one on the bottom of your screen. It's got the people on it. Type your question in there, and we can make sure he sees it for Q&A. Back to you, Lars.
Fantastic. The slide has loaded finally. That's great. I'm hoping you see it before me so you can at least already start reading. Otherwise, you have to wait with me. So here's the master observer. So I'm to quickly look into that as well. As I mentioned, we have the region observer, which I mostly handle today. But the master one is very similar, has all the master-related events, DDL-type calls, like create a table, add a column, all of these things that you can do on the master side, on the data definition language side, region management calls like move and assign. A lot of those calls that you do on that end, you can basically intercept with the same thing. You have a pre and post hook, so you know this already, and you have a specialized environment that obviously in this case is the master environment. The master environment follows the region environment where you have a specific addition to the base coprocessor environment. In this case, you have an extra method called getMasterServices. And the getMasterServices, which is listed in the second table on the page, is the one where you can talk to master-related resources. For example, you can talk to the server manager, which is the one where you can talk to the live servers. You can have access to the executor service where you can run things in the background. So the master has a lot of additional functionality, and so that gives you access to all of these resources on the master side. So that's the master environment. So let's move on. Hopefully, yep. Master services. Quick one, I mentioned this, be careful with those. I mentioned what you can do with them. You saw the list there, so you can access all of the resources, like can modify the assignment plans and things like this. So it's a very powerful thing on the master side, but be careful, similar to the code on the region side, where you can disable splits for everyone. You can do things here on the master side that can render the entire cluster useless because you're doing something that interferes with it. So as an example here, I have a master post hook where I implement something. It's a bit hard to read, but if you look at the, I'm implementing the master of observer class here. In this case, actually, there's a base master observer which I can extend from. I'm implementing a post create table. So that I'm overriding the post create table, which gives me access to information. So I can do what I do here. I say I'm getting handed in the region info, so I can retrieve the table name, and I can say I can do something with the table. In this case, I want to create a directory in HDFS that matches the table name. So I'm taking the table name, postfixing it with -blobs, and then or -blobs, and then creating a directory using the master file system class from the context. So that's an example. Again, I'll just move over that a bit quicker, that you can use to create. And here's an example. I'm creating a table. I deployed that coprocessor. I'm creating a table, and the table is called test table. And when I look at the HDFS, you can see there I created, it automatically created a HDFS directory next to it. That's interesting. I had this idea of this HBlob store where you can store large binary blobs next to HBase, and this would create the tables, the directory. So you, instead of having this to do this with a separate call, as soon as you create the table, the directories would be created. But that's just an example. Endpoints, we talked about the observers now, the region and master observers, and just looking at the endpoints again, we have these, as I said, extending the RPC layer of HBase, adding dynamic calls to it, so you can actually then do whatever you like from the client side, invoking new functionality on the server side. You have to implement this coprocessor protocol, and you have to either address a single one or multiple ones. So that's sort of bringing this back up. To implement one, you just have to extend the coprocessor protocol and define your own protocol and extend this base endpoint coprocessor. So there's an example here again. I can show you the row count protocol. So I'm defining a protocol which is an interface, extending coprocessor protocol. I have a get row count, I have a get row count with a filter, and a get key value count, which is not just counting the rows, it's actually counting the columns, like all of the columns across all of the rows. So that's a different way to count. So these are the three methods that I declare. That's the protocol. And now I'm going into the code. I'm actually implementing the base endpoint coprocessor with my own class called row count endpoint. So that implements that protocol. You can see this there, implements the row count protocol that I just defined before that. I have this internal get count, which takes the filter or not, and counts using a scan. You can see it creates a scan and iterates over, hang on, the next page. It takes the environment and gets the internal scanner from the region. So you can see this there. I'm calling environment.getRegion.getScanner, and then I basically have everything I need to iterate over the region I'm living in. So this scanner will see only the region I'm living in. So that's one-to-one mapping. And now I have to implement, this thing goes through the scan and does the count and returns the count. So that's just a helper. Now, this is being used here in this actual implementation of the interface. So this implements the actual protocol. In this case, I have a get row count with a filter, and the get key value. And you can see I just call internally my get count, either with a filter or not. And I might include the columns or not. But all I have to do here is just count, scan my table, and then return the value. So that's that. And on the client side, I have two choices to invocate this. I have either the coprocessor proxy or coprocessor exec. The difference is coprocessor proxy gives me a proxy to my method, so I have to invoke it with a separate call. Coprocessor exec goes through ranges of a single row or ranges of rows and synchronously but distributed goes out, calls the remote function, returns the result, and I can do something. And there's two helpers, the batch call and the batch callback, that you can use to either implement your interact with the remote functionality, and the callback to react when the call comes back. So you can wait and say, when I get the callback, then I do something with the result from the server. So here's a picture of how this looks like in terms of call. The client A calls the exec, so it goes through a thread pool, calls all of these functions and returns the results. And the client B, in this case, uses the coprocessor proxy by calling a single row and a single region in one region and returns the results. So the proxy, the difference is the proxy always can only talk to exactly one region, while the exec can talk to the entire set of regions, so like a range of regions by using a range of rows. So there's two ways to invocate those coprocessors. Here's an example, invocation by execution. So I have this call there. In this case here, I'm defining the table coprocessor exec, and within that call of the exec, I have to declare an inner class, an anonymous inner class, and there's other ways to do this, but this is like one way to do that, where I say, okay, I implement the call of that batch, which calls the counter dot get row count. Counter is the instance of my row count protocol, and row count counter dot get row count invocates the method that we just saw earlier on the server side. Does the scan, returns the result. So in my client implementation, I just have to wrap this into this call and execute it. The second part of that function is straightforward. I just iterate over the result and print this out at the end. So that's basically just printing the results. This is how it looks like. I'm executing this on my test table. For example, here I have the two different regions, one with the start region and the end region here. So two regions in this case with 2 rows. Again, these examples are in the repository. You can execute them. You should get exactly the same results. The first region has 2 rows, and the second one has 3 rows. So that's basically how you can talk to them. And the other invocation, basically by proxy, just to wrap this up, is using, sorry, let's jump there a little bit, sorry, this one. Invocation by proxy, you do a similar thing. You use your row count protocol, you call table coprocessor proxy. It returns the proxy to you, which is then wrapped into this row count protocol instance, and you have to then, in a second call rows and region, for example, equals protocol.getRowCount. And then it goes out and executes this on this particular region in this case, region. And you get the results back the same way. So again, these are the ways to invocate. To either have the thread pool using Exec going over all of the regions, or you can create the sort of proxy and you can talk to the proxy and talk to it. This is pretty much given our time for today. Is all I can really show you here. But just talking about a few more ideas or so is that what you could do with coprocessors, for example, things that I always wanted to try out but never had the time to, is, for example, accounting. You could use coprocessors to account interactions of a client with the server. So you could, for example, say you control how many updates a user is allowed to do, how many rows he's allowed to create, and then you can have a method that you can reset that quota, or you can enforce this quota by saying, I'm canceling out every operation of this customer because he hasn't paid or whatever it is, or he's not trustable, and tell that the system, this user is not allowed to save. And then what you need to do is you can hand in the user with every call to the server and then use the coprocessor to react to it and check the quota and take the appropriate actions. Secondary indexes, that's a question as well, is just going through the question now as well. Secondary indexes, so the way you use coprocessors for that is that you hook yourself into either the pre or post call hook of the put call, and then you can update the secondary index. There is work being done, or there's not work being done, there's being discussions going on how to implement this best. There are a couple of open JIRAs if you're interested. Some of them are actually using in-memory structures. Some of them are using secondary tables. So it's always this, with secondary indexes, there's always this question, do I use a separate table or do I use an in-memory structure and update that? Because we had in the past what was called indexed HBase, which was in memory, and we had something that was called indexed transactional HBase, which was using secondary tables. Both could be possible with coprocessors. You still have to deal with locking and keeping things consistent or so. You're still moving only app code into the server side, but there's much better chance to be able to lock things on the server side. You cannot really see the coprocessors as a replacement for transactions. This is not what they do. So if you want to have something that guarantees that for every operation that you do, for every put, the secondary index is consistent, then you need to add something into the coprocessor that does something like Percolator does for Google, where you use a distributed locking or whatever it is that is based on other columns in each row to control that something is really being done. So it's hard to answer in a short answer is like a whole thing on its own, but I'm saying coprocessors do not give you automatic consistency across multiple across rows or multiple tables. That is something that needs to be added as well, or anyways, no matter how you do this. But if you were to move this into the server side, then you can just say on the client side, oh, I'm just adding this new web page, and the coprocessor will take care of updating the secondary index or the Lucene search index for you automatically. But the complexity of that is still given, so you still have to solve this somehow on the server side. So that's interesting that this is not really helping you that much there. So there's another question: what you can the current and planned restrictions to the HTable handle that you retrieve from the coprocessor environment. I think let me recall this. I don't have this in the top. Can't recall it entirely. I think there's a couple of operations that you can do with HTable. For example, split or non-split. You could split. No, I have this documented. If you look in the book, I have to actually point you to this one. I don't have this right now in my head. Don't know this off the top of my head. But there's a few operations that HTable doesn't make sense to do this on a single region, and therefore that functionality is just voided in that instance. But in the future, there might be more restrictions being built in, or more security layers or security functions that you can only go through this HTable that you get through the environment to do your work. Then we could restrict this in a way that we can make sure that user code cannot harm tables or so. So it's just a good way to get started with. But as I said, if you want to know what the restrictions are, you look either into the code or you need to look into the book. Basically, it's documented there as well. And general advice on when and when not to use coprocessors. I think the coprocessors are adding complexity. So sometimes it's better to do things on the client side, because then you don't have to deal with moving code into the server. Also, if that is quite involved, if the coprocessors are quite taking a lot of resources away by doing lots of scans, for example, you can end up in a situation where the code that you deploy is actually harming your performance. So because there's no accounting for CPU or resource usage in general on the server side guarding the coprocessors. You could have coprocessors that just kill the performance of your server. So you have to, if you can't control this somehow, it's a dangerous game. So test this very carefully. So currently, where to use and where not to use, I think if you have functionality that you don't want to replicate on multiple clients, think about coprocessors. So you can move that into the server side and make use of it in multiple clients. For example, the one thing that is being implemented on top of coprocessors that will be in HBase is security. So we will have full Kerberos integration with HBase, so that you can control who's accessing which data. And currently, I'll say on the table level, you can say this table is only accessible by the group developers. And the access to that row is controlled using a system coprocessor, a mediator, which allows or denies access. So mediators are a good example. Filters are a good example. Aggregation functions are a good example, where you aggregate data first before you send it down the wire. For example, sums or averages across a column. That is a great example, and there's already an implementation for that in HBase. So there's a lot of things you can do that you need for multiple clients. As soon as it's only for a single client, then it might not be worth the complexity, and you have to just toss a coin.